Hi, I'm Spring, and this is my Lab 3 video report for Physics 2211. So in our mini table of contents, like always, I will first cover the principles of Newton's second law and the universal law of gravitation, and then apply it to the computational model in glow script. Doing those calculations will get us to the purpose of the lab, which is finding the mass of the black hole with our initial values of the star's mass, position, and trajectory. Lastly, I will draw conclusions and address the given questions and any assumptions I make in the lab. So we are still using Newton's second law in this lab, which is actually just the momentum principle in terms of the change in time to be very, very small. So we use the derivative of momentum split into the parallel and perpendicular parts, or components. dp over dt equals the net force, which equates to the same thing of the parallel and perpendicular parts, helping us calculate the black hole's mass. And then on the right side, Newton's law of universal gravitation also helps us solve for the net force because we are assuming the only force is the gravitational pull of the black hole. Setting the two equations we have on each side equal to each other will give us the one unknown, which is the black hole's mass. Cool, and when you run this program, you'll see the star orbiting around the black hole, and that green is a trajectory. And there are three arrows representing the net force, and then the parallel and perpendicular components. And then the values are shown below. Looking into the glow script code, our initial conditions like the gravitational constant and the star's mass are set and will be used in our next slide. Delta T is the number of seconds in a day, which was provided with the instructions. And then this next chunk of code shows us how we will use those initial values. We will first calculate dp over dt and set this equal to the net force. Then we will calculate dp dt parallel, although we could do the perpendicular part first. Simply subtracting either dp dt parallel or perpendicular from dp dt gives us the other part. And because F net is the same as dp dt, the parallel and perpendicular components are also equal to each other. Finally, we are able to calculate the mass of the black hole with the equation in red, using both Newton's second law and the universal law of gravitation. And here is the final calculation of the black hole's mass. I averaged the over 400 iterations of the computational model and found the mass to be 1.90432 to the 34th kilograms. Additionally, the net force and parallel and perpendicular values are given. Lastly, I wanted to discuss any assumptions or potential errors of the computational model. Although the sample size is huge for our mass, the average still isn't the true value of the black hole's mass, and basically we'll never know with this model, so altering it may give us a better prediction. And since there's a slight difference between values, there's almost a wobble in the values if you were to imagine the values on a graph. This wobble has room for error, so reducing the difference between the values could give a better predicted mass. So what does that mean? Well, mathematically, net force and the rate of change in momentum are the same since F net equals dp over dt, but we cannot use them the same way when solving for unknowns. They are measured and calculated in different manners, like in our experiment where we use dp dt instead of net force, because we only have the star's mass, delta t, and its trajectory data. The net force can be thought of as the cause of the star's motion, and therefore a change in the star's momentum, which is an equivalent quantity. Similarly, the parallel and perpendicular parts of net force and dp dt differ in this way. They both represent the star's motion, but the force components are causing the star's components of dp dt to change too. And then what if the black hole was replaced by another one, but the motion of the star was the exact same? Well, we would not be able to tell if it was replaced if we performed this experiment on the new one, because our calculations would yield the same mass. The mass is dependent on the star's trajectory, and therefore it would be impossible for the new black hole to have a different mass.